Hello, I am Dr. Mrinmoy Dhar. I have done PhD in Mechanical Engineering from Indian Institute of Technology, Kharagpur. In this video, I will first introduce hydrodynamic and thermal boundary layers. Then I will talk about boundary layer flow analysis. So, first, let us try to understand what is hydrodynamic boundary layer. In the top figure, you can see that a uniform fluid of velocity u infinity is approaching a flat plate. So when this uniform velocity, a free stream is approaching this flat plate, when it approaches the plate, the fluid particles which comes in contact with the flat plate, that comes in equilibrium with the flat plate, and at this point, and which fluid particle is in contact with the flat plate, their velocity component, x component velocity of that particle becomes 0. As you can see in the top figure, u equals to 0 at the flat plate. But the free stream velocity was u infinity. So if we move in that upward direction, the velocity in the upward direction keeps on increasing, and this occurs due to the viscous effect. So the height up to which this velocity increment from u equals to 0 to the free stream velocity, this height is called boundary layer height, and this effect is felt within this boundary layer zone. This zone is actually called viscous zone, and outside this boundary layer, the fluid flow is not feeling any viscous effect, or rather we can say that the fluid flow outside this boundary layer is not feeling the effect of the flat plate. This is actually inviscid zone. The boundary layer edge, as you can see the blue curve, velocity boundary layer edge, this is actually demarcating the two zones: boundary layer zone, that is viscous zone, and outside the boundary layer zone, which is inviscid zone. Actually, when the velocity at the flat plate is 0, it increases till the free stream velocity. In reality, it has been seen that it cannot exactly attain the free stream velocity u infinity. It almost approaches free stream velocity within less than 1% error. So it has been considered that at the boundary layer edge, it equals 0.99 multiplied by u infinity. So this is about the hydrodynamic boundary layer. And if we see that with the advancement in the x direction, the boundary layer height keeps on increasing. So this boundary layer height is here denoted by delta, which is a function of x. This delta increases with the x direction, and this delta is this behavior of this delta or boundary layer height or boundary layer zone is different for laminar flow, and it is also different for turbulent flow. This is advanced topic. So for now, we just understand what is hydrodynamic boundary layer. Next, we look into thermal boundary layer. In thermal boundary layer, here the free stream velocity which is approaching the flat plate, that is at uniform temperature at let's say T infinity, and the flat plate to which it is approaching, it is having with an uniform temperature, say surface temperature is Ts, which is uniform throughout the flat plate. Now one may think that where this kind of situation may arise. that plate, it is having a constant uniform temperature. So this can be in experimentally we can arrange this situation by keeping a plate above a layer of above a fluid which is at saturation temperature, which say water at 100 degrees centigrade. Water at 100 degrees centigrade is at boiling temperature. So throughout the flat plate, which plate it is surrounded, the flat plate is surrounded by this from the bottom, say by the water at 100 degrees centigrade. So the flat plate will be at constant temperature throughout. And in this case, we are considering that general case that the flat plate is at temperature, uniform temperature. This flat plate is isothermal plate. It is at Ts, and this we considering that the Ts is greater than the free stream velocity T infinity. So there is temperature difference, Ts greater than T infinity. So when this T infinity, free stream velocity, free stream fluid of uniform temperature T infinity approaching the flat plate, here also like the hydrodynamic boundary layer, there will be also formation of thermal boundary layer. Here the fluid particle which is coming in contact with the flat plate, that will also come in equilibrium with the flat plate temperature. So there at that point the temperature of the fluid particle will be the same as the flat plate. So T at the flat plate will be Ts, but the free stream velocity, free stream temperature was T infinity. So in this case, as Ts is greater than T infinity, as we move towards the upward direction, if we look at the temperature distribution profile in the bottom in this slide, the bottom, if we look at the bottom figure and that yellow curve, the T at say a flat plate equals to Ts, and when we move towards upward, the temperature decreases, and at the edge of the boundary layer, thermal boundary layer, here it becomes at T surface minus T at that point divided by T surface minus T infinity equals to 0.99. So this way temperature at the boundary layer edge is defined. So here the boundary layer edge, thermal boundary layer thickness is defined as delta surface T. This delta surface T is also function of x, like delta for hydrodynamic boundary layer. Delta is from the figure you can see that delta T, thermal boundary layer thickness, function of which is function of x, this delta T increases with x. So this is the preliminary discussion about hydrodynamic and thermal boundary layer. With this introduction, we can move to the analysis of boundary layer flow. In the boundary layer flow, what we see that this boundary layer flow are analyzed for finding out velocity profile, temperature distribution. Then if the flow is convective heat transfer is occurring, then the convective heat transfer coefficient H, Nusselt number. This are the objective of analyzing boundary layer flow, to find ultimately these are the solutions of this velocity, temperature, this will be found out. So for this is analysis, first step is to simplify the governing equations, and for this what we do, this is called boundary layer approximations. This is very important step for analyzing any boundary layer problem. So in this video I will not go for analyzing for finding out the solution for velocity, temperature. I will only show how the boundary layer approximations are done. My objective is to just to conceptually make can conceptually make clear the approximations, how these approximations are made. Let us try to understand uh, step by step. For this boundary layer approximations, we have considered very simple case. So assumptions here made are state the flow is steady state process. Constant fluid is having constant property. Flow is laminar. There is no body force. So for these assumptions, here is 2D flow over a flat plate with where free stream of velocity u infinity and temperature T infinity is approaching a flat plate. So here was T surface, as I mentioned earlier, Ts greater than surface temperature greater than free stream temperature T infinity. So the governing equations are given in this slide. First equation is continuity equation. Second one is x momentum equation, and the bottom equation is the energy equation. So these are the governing equations. I'm not going to the derivation of these governing equations. Here my objective is to show how the boundary layer approximations are done. So that we will see now. So see, continuity equations, only two terms are involved. So there no simplification is done. So what simplification can be done, that are in the x momentum equation and energy equation. So let us see that. So in the x momentum equation, first we look at the pressure gradient term, the first term in the right hand side of x momentum equation, minus 1 by rho del p del x. This pressure gradient term can be approximated like this, dp infinity dx. What is this? Let me just explain it. This boundary layer thickness is assumed to be so small that the whatever pressure gradient is felt inside the boundary layer, that is equals to the pressure gradient outside the boundary layer. This is due to the boundary layer thickness is small. This has been, these approximations are made, is made due to the considering that the boundary layer thickness is small. So pressure gradient del p del x is same as the dp infinity dx, means pressure that imply that the pressure, there is no pressure variation within the boundary layer thickness, means along the vertical direction or y direction. So in the vertical direction there is no pressure gradient. That means del p del y is not there within the boundary layer. No, this is pressure is not varying along the y direction or vertical direction. Pressure is only varying in the x direction. So since this pressure is varying only in the x direction, so del p del x can easily be written as d, means in total and not partial derivative, dp dx, and this dp dx can be replaced by dp infinity dx. P infinity is indicating pressure outside the boundary layer, means free stream pressure. So this is about the approximation of pressure gradient term. So and if the case the considered is about a flat plate, in that case dp dvx is comes out to be 0. There is no pressure gradient actually, and when the case is like the flow over a curved plate, the geometry, depending on the geometry, this pressure gradient term will be there, and this for flow over a flat plate, this pressure gradient term will vanish. So for the sake of generality, I am keeping this term in this condition dp infinity dx. Now considering the flow case or geometry, flow geometry, this term will be remain in the governing equation or may vanish. Now look at now we look into the other terms. So first look into the left hand side terms of the x momentum equation and energy equation. Left hand side terms. So left hand side terms, there is two terms in the x momentum equation. So first we see here in the first term there is u del u del x. This u is much higher than v. Why it is so? Because in the boundary layer region over the flat plate or boundary layer region, the flow direction is mainly in the x direction. That in the y direction the flow is very less compared to the x direction flow. The main flow direction is in the x direction, so obviously u will be much higher than v. So in the comparison of first two terms in the left hand side, u is much higher than v, but the del u del x term in the first left hand side, first term, one part is u and then multiplied by del u del x. This del u del x is but much less than del u del y. Why it is so? Because there is velocity variation within the small boundary layer thickness from 0 at the flat plate or solid surface to the free stream velocity at the boundary layer edge. So over this small distance, the boundary the flow velocity u is undergoing a large change. So del u del y will be much higher than the del u del x term. So in the left hand side terms, what we can see, u is much higher than v, but del u del x is much less than del u del y. So what is this? Means a small term multiplied by a large term. So the product of the small term and the large term will be a moderate term. So none of the terms of this left hand side of the equations can be neglected. So this conclusion we can make from this discussion, that none of the terms can be neglected in the left hand side of this x momentum equation. In the energy equation, what happens? As I have just discussed, that u is much higher than v, and the other term del t del x and del t del y. Del t del x is also will be much less than del t del y, because here in the thermal boundary layer, the temperature T will be, the variation of temperature T in the upward direction will be much higher than the variation of temperature T in the x direction, because the temperature has to undergo a large change from temperature at the surface Ts to the free stream to the boundary of the temperature which is outside the boundary layer T infinity. So within the small boundary layer thickness, the temperature has to undergo a large range. So del t del y will be much higher than del t del x. So again here the small part is multiplied by a large part. So so what will come out as a moderate number. So again in the energy equation, left hand side terms cannot be neglected. So we have come to these conclusions that so far what we have seen, that pressure gradient terms we have approximated. Then left hand we have look into the terms in the left hand side of the x momentum equation and energy equation. We have seen that the left hand side terms cannot be neglected. This will remain in the final governing equation. So now let us look into the right hand side terms other than pressure gradient term. So in the x momentum equation, there is right hand side last two terms, nu del 2 u del x2 plus del 2 u del y2. Here we have already discussed that del u del x is much less than del u del y, and the reason I have just mentioned, that the pressure has to undergo, the velocity has to undergo a large change over a small boundary layer thickness. So del u del y is much higher than del u del x. So its second derivative will also be in the same, means if del u del y is much higher than del u del x, then its the corresponding second derivatives del 2 u del y2 will also be much higher than del 2 u del x2. With this logic, the term del 2 u del x2 can be cancelled out. So del 2 del x2 term here can be cancelled out. Now look into the energy equation. Here now we will simplify the right hand side terms of the energy equation. We have discussed that temperature will undergo a large variation within the boundary layer thickness. So del T del Y is much higher than del T del X. So its corresponding second derivatives del 2T del Y2 will be also much higher than del 2T del X2, as x component of momentum equation here will also be del 2T del X2. This term will be cancelled out. This term is much less than del 2T del Y2. So with this simplifications, the final governing equations for boundary layer flow comes out like this. Continuity equation, it remains as it is. In the x momentum equations, this here one term from the right hand side, actually new del 2T del x2 term has been cancelled out. So the x momentum equation, the middle one equation, and the middle equation looks like this. And the energy equation, in the energy equation, alpha del 2T del x2 term has been cancelled out. So energy equation, the bottom equation in this slide looks like this. So these are the simplified boundary layer equations. With these equations, one can go for further analysis and can ultimately find out velocity distribution, temperature distribution, and then for analysis of heat transfer for flow problem, convective heat transfer coefficient or Nusselt number. These things one can find out. But for doing this, the further study, the basic step is to simplification of the boundary layer equations, and I have just shown how to do that. Boundary layer approximations. This is called boundary layer approximations. So with this video I am going to conclude. Thank you very much. I will make more such videos, and for this I will appreciate your love. Please like this video and comment on this video, and also do not forget to subscribe to this channel so that I get motivation to make this kind of more videos. Thank you.